request your honor to grace the chair of President of the webinar on today and inaugurate the meeting. Professor Raut.
Congratulations to everybody who are present in the webinar organized by Department of Chemistry of Sadhu Godeshwar Mahavidyalaya. On this occasion, we have Dr. Santosh Kumar Ratha, the guest as well as the key person of the seminar. I welcome you, sir. Professor Ratha is the process integration engineer of Advanced Packaging and Applied Material Technology, Singapore. I again welcome you, sir. Now I request the head of the department, Dr. Subhash Chandra Sahu, to continue the webinar. Thank you.
Thank you, sir. Warm reception to all of you in the digital decorated platform. Respected President of the webinar, esteemed chief guest of this harmonious occasion, academicians from the different colleges of the state, faculties, participants, and my dear students. I, on the behalf of Department of Chemistry, warmly welcome our chief guest, Dr. Santosh Kumar Ratha, Process Integration Engineer, Advanced Packaging, Applied Materials Technology, Singapore, to the one-day international webinar on materials in electronics packaging and introduction to underfills and epoxy mold compounds, organized under the aegis of Department of Chemistry. In the present scenario of the age of revolution of science and technology, with special reference to materials in electronic packaging, such an emerging topic will immensely open different facts of applied chemistry, so that it will stand as a ray of hope for the welfare of the mankind, as well as the academic and scientific fraternity. Professor Daita Raut is a man of physics with profound knowledge, sincere, honest, dedicated man in every respect. I am proud to get the opportunity to avail this personality on the webinar. I deem it privilege to deliver the introductory facts and facets of our chief guest, Dr. Santosh Kumar Ratha. He completed his bachelor degree in science from BJB College, Bhubaneswar, in the year 1989, and master degree in science from Utkal University, Bani Bihar, Bhubaneswar, in the year 1991, and highest degree of education, that is PhD in material science from Material Science Center, IIT Kharagpur. He published 20 research papers in international journals. He joined as research associate in IIT Kharagpur from May 1997 to August 1998, and worked on synthesis and characterization of water-soluble polymers based on polyacrylamide grafted polysaccharides, and studies the application of water-soluble polymers in drug reduction and flocculation. Joined in Cosmo Films Private Limited, Walju Industrial Estate, Maharashtra from September 1998 to January 1999, and work on testing and development of products based on bi-auxiliary oriented polypropylene films for application in lighting. He joined as a research fellow at Nanyang Technical University, that is School of Material Science and Engineering, from February 1999 to January 2004, and work on thermal and radiation curing polymers, and also handle all modern equipments and techniques like DSC, MDCSC, PGA, TMA, DMA, FDR, UV, visible, light scattering, chromatography, etc. Worked as a staff scientist at Cookson Semiconductor Packaging Material acquired by Panasonic Electric Works from February 2004 to March 2011, and formulated epoxy mold compounds for various applications from commercial point of view. Worked as principal engineer at Modular Technology REC Solar Private Limited, Singapore from 2011 to 2018, and to define the material specification of modules and also evaluation and implementation of thermoplastic and thermoset based materials such as PET and polyolefins as encapsulation materials and PV backsheets. Joined as principal engineer at Heras Materials Singapore Private Limited from 2018 to October 2020, and worked on development of solder fluxes and pastes, and also developed silver-based non-pressure sinter pastes. At present, working as process integration engineer, advanced packaging, applied materials technology, Singapore. It is our proud privilege to have such an erudite of chemical science in the pursuits of highly academic research and development expert. Thank you, sir. Now, I have the pleasure to request Srijukta Ratiranjan Sahu, coordinator of the webinar, to deliver the keynote address. Srijukta Sahu.
Good morning. Respected Principal Sir Dr. Daitari Raut, and esteemed Chief Guest Dr. Santosh Kumar Ratha, and respected HOD Dr. Subhash Chandra Sahu, and all the participants joining in the webinar. I am very much thankful to give me the chance to read the keynote of the topic. Epoch.
Yes.
Now I start reading the abstract or keynote of the topic. Epoxy molding compound is one of the most widely used encapsulation materials for electronic packaging to provide substantial protection for the electronic packages. Several new packaging techniques have been developed and new packaging have been introduced. Materials for advanced packaging provides a comprehensive review on the most recent developments in advanced packaging technologies, including emerging technologies such as 3D, three-dimensional or nano packaging, and biomedical packaging, with a focus on materials and processing aspects. With the development of polymer technology, the reliability of polymer encapsulation materials such as epoxy, silicone, polyimide, and polysulfide have been applied as encapsulants for electronic devices. It further achieves better performance in flammability, toughness, and thermal conductivity. Further, it incorporates organic or inorganic additives to tune the thermal and mechanical properties of epoxy composites such as polyimide, graphene, carbon nanotubes, etc. In the manufacturing process, the epoxy molding compound material and lead frame roughness are the main factors that affect the coefficient of thermal expansion and reliability for an automotive device packaged with no delamination in high temperature application. Thank you.
Thank you, Sujukta Sahu. We are here to listen the technical speech in the melodious form of Honorable Chief Guest, Dr. Santosh Kumar Rathod. Sir,
Good morning, everyone. Can you hear me?
Sir, please continue, sir.
Okay, so good morning, everyone. That was a very elaborate introduction, and I'm very much thankful for this opportunity to speak about epoxy compounds and other materials in electronic packaging. And I'm very much thankful to Dr. Raut, Dr. Sahu, and the academic community of Sadhu College. And I would like to thank you, the entire community of Sadhu College, and also the students and the academic staff. So with this, let me start sharing my screen. Please tell me if it's available. Is my screen coming?
Sir, it is clearly visible, sir. Please continue.
Okay, so the topic for today's discussion is materials in electronic packaging, and I'll be talking about epoxy mold compounds and underfills. I realize that this topic is a very broad topic, and within the short time that we have, we may not be able to cover everything. So probably I'll rush through some of the things, and then at any point of time, if there is any question, please stop me and please ask me questions. And sometimes I speak fast, so if that is not keeping pace with the slides, please stop me and ask questions. Here is the content. I'll provide a brief overview about the IC manufacturing process, and I'll talk about the materials in the electronic packaging. Then I move over to epoxy mold compounds. If time permits, we'll talk about underfills, and I would like to keep some time for questions and answers. Okay, so let me start with a very basic thing. For example, I mean, each of us, everybody that is tuning to this Zoom invitation and Zoom meeting now is either dialing through a computer or dialing through a mobile phone. And what I'm showing here is image of a mobile phone. And if you compare the power of the mobile phone today, if there is iPhone or any smartphone that is being used to dial into this presentation, imagine this mobile phone was built using the technology that was available in 1980s. So I have put some numbers on the right. So if you build this mobile phone using the technology of 1980s, it will cost us roughly $110 million. $110 million. And the size of this phone will be at least 14 meters. And the power it will consume is roughly 200 kilowatts. And that amount of power is sufficient to power 2 Tesla Model X cars. That is using 1980 technologies. And if you compare the same thing today, using the today's technology, I mean, you all see the phone is typically a few inches long. And the cost of the phone is less than $1,000. And the power it consumes is less than 1 watt. So you can see the contrast, the technology in 1980s versus the technology today. So all this has been possible because of innovations in materials engineering and materials process. So process has moved a lot from 1980s by way of using new architectures, new structures, 3D packaging. Instead of going horizontal, package is moving 3-dimensional, upward and sideways. New materials, new ways to shrink. Basically, electronic devices work on the principle of ICs, which is MOSFETs and the transistors. So we always think of new ways to shrink more transistors into the same space, and then advanced packaging. So these are the different ways of transiting from old technology to new technology and continuous improvement of getting more out of same space and same area in the packaging. Okay, so before I go into electronic materials, let me try to speak a little bit about the manufacturing process of IC chips. Typically, IC chips consists of few steps. They call it front end and back end. Okay, in the front end, which is the typical fabrication houses, it starts with the fabrication of the wafer. The wafer is converted into IC chip, and then it goes for wafer probing. Okay, and in the back end, the IC goes for assembly. So assembly meaning, because the IC is a very sensitive device, it has to be packaged into a physical form to be able to be used in the long term. We want the handphone or mobile phone to be usable over a long period of time. So for that, it has to be assembled. And it has to have a lifetime of its own. And finally, it has to go for final test before coming to the market. So this is just in a nutshell. So basically, every IC starts with the conversion of silicon to wafers. On the left, I'm showing the picture of a ingot. This is called silicon ingot. So the purity of silicon used here, this is electron grade silicon. So purity is 9N to 10N. That means it's like 99.99999 to basically 9 nines or 10 nines. This is the purity of the silicon that is used. So the reason is all those electronic devices, the so-called transistors, cannot work with any amount of impurity inside. So the impurity amount has to be very, very carefully controlled. So the silicon is actually grown in very, very carefully controlled pure conditions. So next type is the silicon ingot goes into silicon wafers, and this silicon wafer is converted into devices. So let me go to the next slide. So this slide is a bit complicated. There are too many steps. So let me quickly guide you through the processes. So this is the silicon crystal, which is ingot. The ingot is cut into wafers. So the wafer is being converted to the devices. So what happens in this process? We use the coating of silicon dioxide. This is called a hard mask. So it's basically a dielectric material. So basically, this is to protect the entire wafer surface. The next phase, basically, the pattern is made, which resembles that of the IC device. So basically, you have a light source coming from, and there is a mask. The mask basically allows light to go at a certain place, and it blocks other places. So the pattern of the IC is transferred into the wafer. Okay. The next step, the photoresist is cured, and what you come here is this part of the material is photoresist intact, and this part of the photoresist has been taken out. So photoresist, which is exposed to light, basically gets cross-linked, which is cured, and this part where there is no exposure to light, the photoresist remains soluble. So when using a cleanup process, the so-called development process, using the solvents, this process, this part of the photoresist can be cleaned out. So you have photoresist here, you have no photoresist here. So the silicon dioxide is exposed here. The next process, the silicon dioxide is removed. So once the silicon dioxide is removed, so again the bare silicon is again exposed. So the next process is, in this place, the doping occurs. So basically the IC transistors are carrying a number of P and N junctions. So the PN junctions are actually created using the process of doping. So by continuous replication of PR resist and removal of the PR resist and doping process, so continuous patterns are created. Let me show the next slide. Basically, this is simplifying the process. So basically, this slide is more clear. You can say this is start with the silicon substrate. So coating with the silicon dioxide. This is photoresist. So you can see the UV light is actually being exposing to the photoresist. So this part which is exposed is hardened, and this part which is blocked, this remains soluble. So the next process, this part is easily removed. So the hardened part remains, the non-hardened part actually gets removed. So eventually what happens? So photoresist remains here. So this part of silicon dioxide is removed in the next process. So now the silicon surface is actually exposed, and then the next process is, in this process they actually dope the silicon surface with the N type or P type dopant, and that is when the PN junction is created. So next slide I'm showing similar thing. So after all these processes, so basically this is an N type silicon and the dope with P type dopant, so PN junction is created. So this PN junction is what it looks like in the form of final device, and this PN junction is connected through metal layers. This is in a nutshell how the IC device is created. So here I'm showing a final wafer where the IC devices have been created, and each of these units actually resembles an IC device in the final form. And the side of the wafers, like peripheral area, those are the so-called wastage, because this is a circular wafer, so it doesn't form a full device. So this part of the wafer gets wasted. And these are the scribe lines. So eventually the wafer is cut into individual dices, which goes for final packing. Okay, so basically this is where you end up. In the previous slide, this is where you end up. These are the devices created on the wafer, and the devices need to go for packing. Okay, so what happens? The devices are then removed and then go for inspection. Can you see my slide? I'm seeing interruptions once in a while. And then these individual slices actually picked up and then go for different types of packaging. So what you see here is basically a lead frame. Just now it was described by Mr. Sahu that this is a lead frame based package, which is basically this called DIP. Finally it goes for final test, and then this is go for marking. It's not moving. Okay, so this is the typical appearance of a motherboard in a computer. So you can see there are various devices and various packages inside the computer. So these are the so-called lead-based packages, lead frame-based packages, and then these are the so-called substrate-based packages. Okay, so depending on the type of package that is used, there are some are lead frame-based and some are substrate-based. Okay, so this is called packaging hierarchy. So we start from the wafer, and this is the final motherboard. So wafer gets converted to chip. Chip is connected to the first level packaging, which is either lead frame based or substrate based, and those packages are then converted into a PCB, and the PCB goes onto the final motherboard. So this is the flow of packaging from starting from wafer to chip all the way up to motherboard. Okay, so this was an introduction about how the IC chip is being formed and how it goes for packaging. So now you go into the so-called materials in electronic packaging. So what I'm showing here is imagine this is an electronic device, and what are the different types of materials? It starts with, I mean, this is a multi-billion-dollar industry. It starts with board assembly materials, like things are like solder cream, conductive adhesives, non-conductive adhesives, potting compound, conformal coating. These are the different types of materials. Then on the other side, we have polymer thick film, glass substrate, polarizer film, liquid crystal polymers, and alignment films. Then on the wafer side, we have silicon wafers, photo masks, wet chemicals, dielectrics. On the packaging side, we have lead frames, molding compounds, we have organic packaging substrates, we have die attach and underfills. And we also have thermal interface materials, heat spreaders, phase change materials, solder mask. So this industry is a multi-billion-dollar industry. There are so many materials coming to picture to form a final electronic packaging component. So not only fab houses, there are a lot of supporting allied industries which are supporting this segment to form this entire value chain, starting from wafers all the way up to computers or mobile phones or all the IC devices that comes to market. Here is a short table that talks about different materials and the so-called different manufacturers. So for the sake of brevity, I have shown about 15 different materials. So these are different materials like solder preform, conductive adhesives, non-conductive adhesives, polymer thick films, silicon wafers, and these are the representative manufacturers. So as I said, this is a booming industry, and there are multiple industry houses supporting this manufacturing, and this is a multi-billion-dollar industry. It's not moving. Just give me a while. My slide is not moving. Hello.
Hello, sir. Sir.
My slide is not moving. Sorry. Okay. So basically here, I'm showing an example of a package. Basically, I'm trying to zoom into. So what we are seeing here is an individual package showing the presence of different materials. So you see here, this is the so-called BT laminate, and then these are the solder balls, and we have dielectrics inside, and these are the so-called vias. Basically, this is the connecting paths from this die to this outer connection. Then we have a wire bond from this die to outside, and then on top of this die we have another die sitting, and between this die and this die we have the bombs, and then this is the underfill material, and this is the another die, and between both the dies you have the so-called mold compound. So you can see this package basically eventually we are talking about formation of IC devices. This is one IC, this is another IC. But for these two IC devices to come to market, they need to be packaged. And there are so many different materials in one single package. You can see so many different materials: the dielectric, the bottom die, the solder balls, the top die, the bombs, the older fields, mold compound. Each of these materials need to be integrated into a final form, and each of these final form has to pass the reliability tests. The reliability tests are basically catered to make sure individual components talk to each other, and they can do so over the entire lifetime of this device. So it's a gigantic step starting from wafer all the up to final formation, and the whole industry makes sure along with all the new inventions and new things are happening, it has to be integrated together so that the value chain keeps maintaining maintaining the relationship from end to end. So we are going to electronic packaging now. So when I talk about function of electronic packaging, like we started with the die, and this is our PCB. So this die has to talk to the next level. So when you're talking through a phone, basically the IC device inside is doing its job, and you are able to hear it. There are many multiple functions integrated inside the phone. So first thing is the signal has to be transmitted from the die to outside. And when the die is working, when the chip is working, it produces a lot of heat. And if there's too much of heat, eventually the die may burn, the chip may burn. So the heat that is being produced needs to be distributed and taken out of the package. So that is the heat distribution is one of the roles of the packaging. Next is power. The chip needs power to function, so the power needs to be distributed. And then circuit support distribution is another thing. So in terms of functions of the electronic package, there are at least 4 different functions, and each of these have to integrate with each other for the device to work properly. And that is where when you develop materials for this industry, it has to look into the package, look into the package properties, look in metal properties. So typically metal properties fall into 4 categories: electrical properties, thermal and thermomechanical properties, mechanical properties, and chemical properties. So there is no one set of properties that works for all. It depends on type of package, the type of application, and eventually these materials need to be tuned, need to be tailor-made to meet those objectives in terms of meeting the material requirement before going for final packaging. So, for example, underfill material will have a different set of metal properties than epoxy mold compounds. Epoxy mold compounds will have a different set of properties than a thermal adhesive. And thermal adhesive will have a different set of properties than, for example, photoresists. So different materials, depending on application and end use, will need to be tailor-made into a specific set of metal properties to be applicable for the end application. So with this, I'll get into the epoxy mold compounds. Let me give the brief introduction of epoxy mold compounds. So what is epoxy mold compound? So as the name indicates, there are three terms: epoxy, mold, and compound. So the term epoxy comes from the fact that this metal uses epoxy resins. So epoxy resins is a set of synthetic resins which forms the principal component in these materials that forms the matrix to hold the components of the epoxy mold compound. And the term molds comes from the fact that this is applied in the final process using a process called transfer molding. So during transfer molding, this metal is finally transferred onto the IC packages. That's where the name mold coming from. And compound meaning it's not a single material. It's a combination of many different materials which is compounded before it is being transformed into the final preform or pellet. Hence the name epoxy mold compound. And the way this material looks, it's typically black because it has been formulated to look black. But epoxy mold compounds can also be of different color, like red, blue, green, depending on what kind of color the end use demands. A color can be different. Okay, so here are the key functions of epoxy mold compounds. As you expect, the IC chips are very sensitive, very delicate. So the first thing is the electronic component needs to be protected from the external environment, from the moisture ingress, from temperature, and from contamination. So that's the first function of the epoxy mold compound. Second function is it needs to protect the chip from mechanical shock. You do not want your phone to easily break when you drop it. And it also provides a structural support, and it provides the electrical insulation. And by itself, the mold compound should not be detrimental to the performance of the device. So in addition to providing all these functions, by itself, it should not be detrimental to the functions. So this is a typical composition of the mold compound. So basically it starts with epoxy resins. So the function of epoxy resins is to form the matrix because it contains a lot of different materials. So it forms the matrix that holds the different components. So typical epoxy resins here consists of epoxy crystal novolac, biphenyl resins, dicyclopentadiene resins, and multifunctional resins. Then it has curing agents, which are hardeners, and the process is by cross polymerization. And typical components are polyphenols, amines, and acid anhydrides. Then it has accelerators, which are typical amines, imidazoles, organophosphines, and loose acids. Then it has a lot of inert fillers. So typical inert fillers consist of silica. So silica is the most widely used filler because it first thing is cheap. Second thing, it has a very low coefficient of thermal expansion, and that's easily integrated into epoxy matrix. On the other side, you also have aluminum nitride and alumina because these two materials are very high in conductivity. So for thermally conductive compositions, these two metals are widely used. Then we have coupling agents. So basically what happens in epoxy mold compounds, you are mixing the resins with the fillers, which are silica. So on the one hand, you have an organic matrix, another you have inorganic fillers. So they do not bond to each other very well. So the role of these coupling agents is basically to help them to bond together and form uniform matrix. Then we have a material called flame retardants. The function of this material is to make sure the final composition does not catch fire easily. So typical materials used here are brominated epoxy materials, antimony oxide, phosphate esters, zinc borate, and aluminum trihydrate. These are typical flame retardants used in the epoxy mold compounds. Then we have stress relief agents. So basically these are silicones, butyl rubber, aliphatic epoxide. So these materials tend to reduce the modulus of the material, make it soft. While reducing the city, they tend to make it soft. So these are so-called stress relief agents. Then we have mold release agents, because once you mold at the high temperature, it has to come out. So we have stearic acid and natural waxes to act as mold release agents so that the package comes out easily at high temperature. Then we have coloring agents, which is typically carbon black, but it doesn't have to be black. It can be any other color. And then in that case, we have other colors to be used. This is a typical composition of mold compounds. So here I'm showing basically some chemistry like this is a novo-like hardener. So basically starts with the phenol, reacts with formaldehyde, and then gives rise to the so-called monomethyl phenol. This monomethyl phenol again reacts with formaldehyde to give rise to so-called dihydroxy diphenyl methane. And this goes further polymerization to form this novo-like resin. So this is a very common raw material that acts as a hardener in epoxy mold compounds. The next slide, I'm showing the formation of the so-called epoxy resins. Again, it starts with the phenol. Phenol reacts with formaldehyde to give the so-called novo-like resin. And novo-like resin, you can see these OH groups react with epichlorohydrin so that the epoxy group is introduced here. So this is the so-called epoxidized novo-like. That's called epoxy derivative of novo-like. So on the one hand, you have this epoxy resin. On the other hand, you have the novo-like resin. So these two react together to form the so-called cross-linked matrix in the epoxy resin, epoxy mold compound. And this cross-linked matrix holds everything together that forms the final epoxy mold compound. And here I'm showing some other examples, like this is a orthocrystal derivative, and this is the simplest form of diglycol ethers of bisphenol A. This is another epoxy resin that is very commonly used. Here I'm showing the so-called coupling agents. Basically, imagine this is the silica filler. So silica fillers have some OH groups on the surface, and then silica fillers do not go so well with the organic matrix. So what happens? These coupling agents are in the form of silence, organic silence. So organic silence tend to get esterified onto the filler OH groups. So these form the silanol groups. So you have the organic group on one side, inorganic group on the other side. So this inorganic part joins with the fillers, and this is the organic part which tends to mix well with the organic phase with the epoxy matrix. So basically, the inorganic phase and organic phase bond well in presence of coupling agents. And these coupling agents can have different types of organic groups like epoxy groups, amine groups, thiol groups, mercato groups. So basically, the different types of treatments helps with compatibilization of different types of fillers and organic matrices. Here I'm showing the process of mixing the coupling agents with the fillers and additives. So this is how the process goes. So basically everything is compounded together, the mixing, kneading, cooling, and finally this is how the epoxy tablet comes out. We have a lot of fillers inside the epoxy mold compounds. So the role of fillers is basically, here are the advantages. Basically, first thing, you have typically 80 to 90% of filler inside the epoxy mold compound. So filler being of low cost, it reduces the cost of the material. It reduces the shrinkage because organic materials after epoxy resins, after curing with organic hardeners, they tend to shrink a lot. So by putting a high volume percent of inorganic filler, the shrinkage is reduced. When the shrinkage is reduced, the material tends to have a low stress inside the final package. Improve the toughness, then improve the abrasion resistance, reduced water absorption because organic matrix tends to absorb a lot of moisture. So by putting inorganic fillers, you tend to reduce the water absorption. It increases the heat diffusion temperature, increases thermal conductivity because organic matrix doesn't conduct heat a lot. So inorganic matrix like alumina or aluminum nitride or even silicon dioxide, they tend to conduct to some heat to some extent. So the thermal conductivity of the matrix is increased by putting inorganic fillers. And most importantly, the introduction of inorganic fillers helps to reduce the thermal expansion coefficient. This is very important because typically what happens, the silicon chip has a CT of 2.3 ppm per degree C, and organic matrix, like if you just take epoxy resin and phenolic hardener, the typical CT of that metal is close to 200. So 200 versus 2.3, the CT mismatch is very high. So one of the reasons for introducing a lot of silica filler inside the epoxy mold compound is to bring down the CT to the range of 10 to 15. So by reducing the thermal expansion coefficient, the reliability of these packages is enhanced significantly. So this picture is showing the effect of conductivity on the final formulation by the filler content. So this is the volume percent. So what it shows is for fused silica, it's not very conductive compared to crystalline silica and compared to alumina. So alumina is one of the most conductive additives compared to crystalline silica, compared to fused silica. But then again, it's always a mix and match. Alumina has its disadvantage, fused silica has its advantage. So when you go for epoxy mold compound formulation, it's always a mix and match of the required properties and basically minimizing the undesirable properties. Coming to disadvantage of using the fillers, of course, using fillers increases weight, the density goes up, increases viscosity because eventually the metal has to flow. By putting too much of filler, the viscosity actually goes up. And by putting too much filler, the metal becomes very hard, the modulus goes up, so machining difficulty goes up, and dielectric constant goes up. So these are some of the disadvantages. So basically in this table, I'm showing some of the comparison between different types of fillers. So basically you can see fused silica in terms of conductivity is very low, 1.3. This is one of the disadvantages. Crystalline silica has good conductivity around 14, but the difference is crystalline silica is carcinogenic. So in terms of health benefits, this is not something highly recommended to put in the packages. Aluminum nitride, you can see it has a very high conductivity. So whenever a package requires high conductivity, aluminum nitride is a preferred filler to use in the mold compound. Then in terms of CT, in terms of expansion coefficient, the fused silica is very good. It has around 0.5 compared to other fillers, which are like, you can see the conductivity is very good, but the CT compared to silicon is quite high. This is 0.5 versus 4.4. Ideally, you want a material that is very low in CT, not very high. I think these are the two important properties to take into account. Next thing is electrical resistance, because epoxy mold compound is something that is used as a dielectric material. So you do not want this metal to have very high conductivity. So in terms of resistivity, it has to be as high as possible. So you can see fused silica gives very high resistivity compared to aluminum nitride or even alumina. So again, as I said, when you are trying to formulate a epoxy mold compound, I mean, of course, I can show here. You see here these are different components, but when you try to formulate them, you formulate them against a set of desirable properties. You do not want to have a lot of undesirable properties, and of course, you cannot have everything good. So it's always a maximization of what you want and minimization of what you do not want. So as I said, this is fillers, organic matrix, inorganic matrix, and all other additives need to be optimized in the proper ratio, proper proportion. Here I'm showing some examples in terms of the effect on the coefficient of thermal expansion for different types of fillers. So crystalline silica versus alumina versus fused silica. So you saw in the previous table, fused silica has a very low CT. So by increasing the content of fused silica, the CT of the final mold compound goes down a lot. But compared to that, crystalline silica has higher CT. So yes, crystalline silica has higher conductivity, but it has higher CT, which is not desirable. So again, depending on the type of package, if you need high conductivity, of course, crystalline silica is preferred. But if CT is very important, then fused silica is needs to come to the picture. So here I'm tabulating some of the typical properties of the mold compound. So there is a property called spiral flow. That means how much the material flows at high temperature so that the cavity can fill in properly. So gel time is an indication that after some time metal gets hardened. So at what point the metal gets hardened so that it doesn't flow? Because it doesn't flow, then it will not fill the cavity. So gel time in terms of processing is very important. Coefficient thermal expansion is critical for reliability. So we have two properties, alpha 1 and alpha 2. Basically, this is related to the TG, glass transition temperature. So the glass transition temperature is the temperature basically distinguishes for polymeric materials. It's a very important property. Basically, it's a boundary between glassy and rubbery phase. So the material behaves very different in the glassy phase compared to the rubbery phase. In the rubbery phase, the CT, the coefficient of expansion is very high compared to the glassy phase where the rate of expansion is low. So, for example, if you have metal which is 165 as TG, and below TG the metal rate of expansion is 17, whereas above above TG the rate of expansion is 68. That means the metal is expanding at a very fast rate after TG compared to below TG. Then conductivity is like again depends on the final packaging. So these are some of the typical properties I'm showing. So like then these are typical properties, and on the left side I'm showing the characteristic properties like which are critical from manufacturing point of view and critical from performance point of view. So for the device performance in terms of long-term reliability performance point of view, properties like glass tension temperature, CT, which is thermomechanical properties, thermal conductivity, dielectric constant, all these are very critical from performance point of view. And from manufacturing point of view, things like spiral flow, the shear viscosity, and the KO time, flow resistance are important. This table I'm showing the packaging process. So this is a leaded package. So basically it starts with the lead frame. So we talked about the IC device. So imagine this is the so-called die, which is the IC device, which sits on the lead frame. So then there is a wire bonding. So this wire bonding is basically carrying the signal from the die to the outer side, external side. This is the wire bond, and then this is the molding process. In this molding process, the epoxy mold compound is forming the encapsulation process. So the die and the wire bond assembly is being encapsulated inside the mold compound, and then the next process is basically deflashing. Deflashing the process where there is some compound actually coming outside the package. So this has to be removed. And then next thing is this is so-called trimming and singulation. So once you singulate, this becomes an individual package. So in past few slides, I told you how the IC device is made. And here I'm talking about how the IC device is being packaged inside the final package. And this is the package that goes out to the secondary level where it goes into PCB, printed circuit board, and then it goes to motherboard. This is another type of package. So here, these are substrate type of packages, which is different from lead frame type. So this is an organic substrate. So here is the IC chip sitting, and then basically this goes through a process called plasma cleaning, and then there is a wire bonding, and then after wire bonding, again there's a plasma cleaning because plasma cleaning helps remove the contaminants. Then there is the molding. So again here mold compound is sitting on top of it. So this is different compared to lead frame. In the lead frame process, you can see the mold compound is covering the entire side. The top and bottom of the package is covered by mold compound. Whereas in substrate type, it's only on one side, because the other side, the so-called the ball attach process. So what happens? There are vias below this die. So these connections go through this die pad area. So this is where the ball attach happens, and this will be going on to direct surface mounting on the final package. So in terms of package design, substrate-based packages are different compared to lead frame-based packages. So the assembly process and the packaging process is slightly different. So basically, this after this, these balls go for reflow. Reflow meaning that basically these balls are getting attached to this substrate pad area, and then after this there is singulation, and this unit becomes individual unit go for the final package. A little bit of hint about the manufacturing of epoxy mold compounds. So basically, it starts with the process of weighing. I have told you about the composition of the mold compound. Basically, it's all these components are weighed into a beam. So basically, this is the final material, which is this black stuff is carbon black. Basically, if the mold compound is designed to be black in the final appearance, they put carbon black on top of it. So this is basically putting everything together in terms of weighing the materials. Then these materials go for the high intensity mixing. So this is a mixture. So after mixing, this is how it looks. So this is the starting with carbon material. Then after mixing, this is how it looks. So then this goes for goes into extruder for this metal to be mixed at a very high temperature. So after melting and mixing, this comes out in the form of a metal that actually hot and melted hot material. So then this is chilled and it formed into seeds. So these seeds are actually cooled down to room temperature, and then this is granulated, and the granulated finally form into pellets. So eventually, when this epoxy mold compound is sold to customers who are actually making this process, so they receive these metals in the form of preforms. So these preforms go into the mold here. So I'll show you how the mold looks like. So these are typical molds that use the epoxy mold compounds, and the typical molding process, the molding machines. And in terms of actual molding process, so basically imagine this is the where the die is sitting. These are the so-called runners, and this is the mold compound. Here you basically apply pressure. Once you apply pressure and heat, the metal actually gets molten here. After it's molten here, this metal comes out here. When the die is sitting here, the metal feels it. So this is how the molding process works. So there are two types of molds. One is conventional mold, another is auto mold. So this is how the two process looks. This is the conventional mold, and this is gang pot mold. So basically, this is the pot, and this is the so-called runner. That means once you put the epoxy mold compound here, once it melts, it flows through these runners, and these runners go into the place where the package is sitting, and then it basically fills this cavity. Once this cavity is filled, then mold compound fills the runner, and basically the package is filled and it encapsulates the package. So here I'm showing the basically players in the market in terms of mold compounds. Of course, Japan is at the forefront. I mean, this is the statistics I've taken from year 2000. So Japan is number one in terms of mold compounds. They have a lot of players, close to 70% of market at the time. USA is around 17%, and Korea is around 8%, and Taiwan is around 5%. So in terms of top manufacturers of epoxy mold compounds, Sumitomo is number one, followed by Nitto. So Cookson used to be a big player in USA. I used to work in this company. I put it red because this business of Cookson is no more. This business has been sold out. That's why I put it red. It's no more existing. This business is no more existing. I used to work for this company. Then Taiwan. I mean, there are other small players in other countries. I think there are some hands being raised. Maybe I can answer some questions later. I think let me take a pause here before I go to Underfills materials. Let me pause here and let's answer some questions from the participants. Hello. Sorry,
Hello,
I'm
sir.
rushing too much, I guess.
Hello, sir.
Hello.
Please, sir.
Kuantu.
Please continue, sir.
Okay. So I'll continue the Underfills materials. Okay. So before I continue the Underfills materials, let me ask about something. So how do I hide this part? This part is actually blocking my screen. Is there any way to hide this part? It's okay. Okay, so there is something called coefficient of thermal expansion. So in this, okay. So let's talk about some materials and how they expand at heat. So imagine we're taking different materials: lead, tin, brass, concrete, steel, and all the way up to porcelain. So imagine the original length of the package, original length of the material is 100 feet. And we heat the material by 100 degrees centigrade. So what happens when we heat the material? It expands. So you can see lead expands like close to 3.5 feet. For the same amount of heating by 100 degrees centigrade, different materials expand differently. You can see lead is expanding by 3.5 feet, whereas porcelain expands less than half a feet. So if we convert this degree centigrade per per minute, so you can per degree centigrade, you can see the rate of expansion of porcelain is very small compared to lead. Okay, so in this picture I'm showing some pictures. What it shows is because of thermal expansion during hot weather, the rails are getting bent. You can see rail lines are getting bent. This is an effect of thermal expansion. So when the train is running, there is a lot of friction, and also in hot weather, the rails are actually very hot. So because of metals expanding very fast, when they touch each other, they tend to get bent. On the right side, I'm showing typical on the road side. You can see we always know this. There is always a gap between two slabs, and this gap is there because when the metal actually expands, there is space for it to move in so that the metal doesn't buckle and doesn't break down. So this is an effect where the effect of thermal expansion is actually taken to design. So bridges has to design like this to prevent this effect. So the reason I'm showing this is thermal expansion coefficient plays a big role in the design of IC packages. So with this, let me go to next slide. Okay, so what I'm showing here is this is so-called the flip chip. Okay, this silicon chip, this is substrate, and this so-called these are the bombs. They are made of solder material. Okay, so these are solder pads where this connection between the chip and the substrate, these are the connection happens. So this is at room temperature. So when we heat it, because for these to bond, these are actually solids, so it has to be heated to become molten. When it becomes molten, it will form a bond between these two and connect the two materials. So when we heat it, typically we heat it beyond 240 degrees. So this metal actually melts. When this is molten, the metal is the assembly is at a temperature 240 degree. So at that temperature, this gas expanded and this gas expanded. But the expansion coefficient of silicon and the substrate are not the same. Like I showed here, you can see the rate of expansion of silicon and porcelain are not same. If this is expanding at a faster rate, this is expanding at a slower rate. Okay, so similarly, the substrate here expands quite a bit compared to the silicon. But these guys molten, so that's fine. So at some point after the reflow and bond formation has occurred, the assembly has to be cooled down. So when you cool down, what happens? This metal solidifies below 180 centigrade. This metal will solidify. When it solidify, this metal which is originally expanded will contract, and when this contracts, this also contracts. But the rate of expansion and contraction is not same for both. So this contracts at a faster rate compared to this one. So what happens at 180 degrees centigrade when this metal has already solidified and this is still contracting? So this cannot remain straight anymore because this will not allow it to contract further. So what happens in the process? This metal actually becomes bent. So when this metal becomes bent, there's a lot of stress being held at these solder bombs. So this is the so-called flip chip package. So history has shown if you don't have anything in between, these solder balls tend to carry a lot of stress after the process has gone through reflow and after the bonding has happened. So the epoxy mold compound is something that came in between to fill this space and distribute the stress. Okay, so with this, let me go to epoxy mold compound. So this is the chip, this is the substrate, and these are the bombs. So you can see there is a metal in between that's called epoxy mold. This is called the underfill. So this underfill is a composite material. It's again made with epoxy resin and with additional fillers, and again it has some agents like flow agents, adhesion promoters, and dyes. Okay, so the function of the underfill is basically to reduce the effect caused by the city mismatch of the chip and the substrate. So in principle, the underfill that goes in carries a city very close to that of the solder balls. So what happens? The stress that is carried out by the bombs is eventually distributed and made uniform within this underfill. So the stress that was originally carried by the solder bombs is actually distributed within the underfill, so that when the assembly goes for reliability, it can last much longer compared to an assembly without the underfill. So in terms of composition, the underfill and the epoxy mold compounds are very similar. Both carry epoxy resin, both carry fillers, both carry additives similar to epoxy mold compounds. The only difference is in the size of the filler and the amount of filler. Because in the design of the underfill, there are two critical factors design in the design of underfills. The adhesion of the underfill to the chip and the substrate, it has to adhere really well. The adhesion has to be very good, and at the same time, the CT, the coefficient of thermal expansion of the underfill, has to be very close to that of the solder. So let me show the desirable properties. So the key thing is CT. CT is 18 to 30 because CT of the solder is around 26. So the coefficient of thermal expansion of the of the solder has to match that of the underfill. That is number one. And number two, the adhesion. Adhesion has to be very good. So these are the two critical factors, and rest of the properties are actually very close to in terms of design of the mold compounds. But for the underfills, these are slightly different compared to mold compounds. So with this, I think I have come to my presentation end. I think I was in a bit of, I think I uh, went a bit fast. So let me take some time to answer some questions from the floor. If there's any clarification required on any slide, please let me know.
Hello.
Hello.
Hello. Ganesh किस कहूँ को? Hello.
Hello, sir.
Kuantu.
Please continue, sir. Sir.
Actually, more presentation. I have come to the end of the presentation.
Okay. Okay, sir.
Ganesh sir.
Subhash
Ganesh
sir,
sir.
please unmute yourself and speak, sir.
If there's any question on any of the slides, please let me know. Maybe I was in a, I
Sir,
finished it too quickly.
actually, sir, there is a question in the chat box
Kuantu.
that can we use chromium as a material in electronic packing? A question from Sashwati Das.
Chromium, okay. When you say electronic packaging, basically it depends. I think chromium is used as a material in terms of it's a metal used for metallization. Chromium is a metal, so metal means it's conductive. So if it's conductive, it has to find an application where its conductivity is plays a role. So epoxy mold compounds and underfills are basically non-conductive materials. So yes, chromium as a material finds application in packaging. I think it finds a role in a place called metallization. I mean, as I said, the electronic packaging industry is huge, and there are a lot of different metals is being used as part of the metallization process, and definitely chromium is one of them. Yeah.
ना ना पचार भूले रखना.
Did I answer the question correctly? Hello, any other question?
Hello,
Hello.
sir, please unmute yourself. Subhash
Really?
sir, please unmute yourself. Presentation has been over.
ଏଇଠି କହିବି ତ ମାରିବି
Sir.
Ganesh sir, any other question from chat box?
No, sir. No.
I would like to convey my deepest sense of honor and gratitude to Dr. Santosh Kumar Ratha for his highly illuminative and elucidative talk. Sir, your digital presence in our department has really enlightened the members of the department for further scientific and academic exploration. Presence of participants has also made this gallery of wisdom so successful. Now, I request Ms. Gayatri Sahu, coordinator of the webinar, to give the vote of thanks.
Respected patron of the webinar, our beloved principal sir, Professor Daitari Raut, esteemed chief guest, Dr. Santosh Kumar Ratha, respected HOD of chemistry, Dr. Subhash Chandra Sahu, respected organization secretary of our webinar, Mr. Nirmal Kumar Naik, respected faculty members of different departments, respected sir, madams, and my dear students. It is my proud privilege to propose vote of thanks on behalf of the chemistry department, the entire fraternity and organizing committee. I would like to thank our beloved principal, Professor Daitari Raut, who inspired us for arranging such an huge webinar. I feel immense pleasure to take this opportunity to propose the vote of thanks to our Honorable Chief Guest, Dr. Santosh Kumar Ratha, who has spared his precious time from his busy schedule to grace the webinar. We are also very much proud to have eminent scholar, a dynamic personality, a voracious reader, and a profound knowledge in chemistry. Sir, your participation in this pandemic situation gives us very grateful. I would extend my hearty thanks to Dr. Subhash Chandra Sahu, the HOD of the chemistry department, for his thought and vision providing inside the webinar. I take this opportunity to specially express my deep regards and gratitude to Mr. Nirmal Kumar Naik for always encouraging us and providing opportunity for organizing such events. My deep sense of appreciation and thanks to all the participants who choose to be live with us and attend this webinar with great enthusiasm and made it a successful event. My sincere gratitude also goes to the organizing committee for taking the topics materials in electronic packaging and introduction to underfills and epoxy mold compound. Last but not least, I thank to our arranging committee, Sri Ganesh Chandra Panda and Dr. Satyaranjan Naik for all the technical support and helping us webcast and webinar through our YouTube and Zoom app. Thank you all for being with us in this afternoon, making the webinar a huge success. Have a wonderful day. Thank you to all.
Dear participants, please fill the feedback form. I have given in the chat box so that we can be able to send you e-certificates. Please fill the feedback form.
Ganesh sir,
Sir,
I will speak.
hello.
So to say, in the way, when and where Dr. Ratha starts and deliberate the speech in the technical form in the modern ways, we learn more and remember his personality forever. Thank you. The webinar is ended. Thank you.
Thank you. Thanks, everyone.
Thank you, sir.
Ganesh sir,
Sir. Sir, I'm ଟିକେ wait କରିବା.
okay.
Participant ଟିକେ feedback form ଟା fill up କରିଦିଅନ୍ତୁ.
Okay.
ହଉ ହଉ ସାର୍ ମୁଁ ରଖୁଛି।
Sir.
ହଁ ଥ୍ୟାଙ୍କ ୟୁ ସାର୍।
Thank you.
ହଁ
ଯାହା ଶାଶ୍ୱତୀ ପଚାରିଲା ଭୁଲ କହିଲି।
Sir ଟିକେ ରୁହନ୍ତୁ ମୁଁ YouTube ଟା